here to talk about Yelp's journey into containers. So what that means is basically how we took Yelp, which is a large company, lots of engineers, been around for more than a decade now. So a company that started, basically not using containers, started in 2004, had a lot of years without using containers, a lot of good years of development, and how we've introduced containers in a way that works really well for developers and makes life better. So just a little about Yelp, some background. Our mission is connecting people to great local businesses. We have about 90 million unique visitors on mobile, 102 million reviews. 70% of our search traffic comes from mobile, and we're in 32 countries. So then a little about me. I'm a software engineer at Yelp. My background's mostly in like system administration and automation, or what you might call DevOps, although I do a lot of programming now as well. And my team's goal is basically just improving the life of developers at Yelp. So what that means is improving the build process, improving the way we test, getting rid of legacy code, things like that. So basically just trying to make it so that developers can work faster, work better, and more efficient. And then so a little about Yelp. We have more than 300 engineers now. We are very much invested in like a microservices strategy. So we have more than 300 services that are deployed across like dev, test, and prod. And we're launching right now more than 1 million Docker containers a day, so at a pretty big scale. So the thing people say when we talk about this is like, whoa, 1 million containers per day. And the point I want to make is that we had a lot of years without launching any containers at all. So it's only in the past couple of years that we've hit this like millions of containers per day. And so the point of this talk is going to be like, how do you go from these no containers, but things still pretty much work, right? Like there's life before containers. And so if you're especially at a large company or a company that doesn't have this history of containers, like kind of a startup that started with them, how do you introduce them in a way that works really well and that just improves people's lives? So yeah, I'm going to start by talking about Jenkins. And so if you're not familiar with Jenkins, first of all, congrats. So this is our Jenkins. And if you have a large engineering department, this probably looks familiar. I just want to point out that these things that I was asked to gray out, these are tabs in Jenkins. These are not jobs. I was originally going to post a screenshot of the entire Jenkins, but it turns out it's 147 pages if you try to print it out. So you have something like 10,000 different Jenkins jobs. And so we have a pretty large infrastructure in terms of like projects that we test. And so test is basically where we started using Docker containers. So because we have all of these different jobs that we want to test, we end up maintaining this massive Jenkins and all these different Jenkins slaves and different this one's running Ubuntu Xenial, this one's Ubuntu Trusty, this one's Ubuntu Lucid. And so all these different environments, and then we need to install system packages for some tests, and some don't need them. And it turns out that containers are a really good way to solve this. So basically what we've done in most of our projects is we have this like two-step testing process, where the first step is just calling Docker build, and then the next step is just calling like run that same container. So most of our projects now have like a Docker file in them, which says, start with this Ubuntu image, add these like 5 packages, add the code, add the testing code, and then run the tests. And so it means we get these really good, our make files are extremely simple. So in most cases, we're just doing, Docker build, Docker run. And the really nice thing about using make files like this is that if your tests pass locally, you're almost guaranteed they're going to pass in CI, because you don't have these extra dependencies like, things like packages are not installed, or you're missing like header or something. So things pretty much just work. And it's really nice because it means if you're on like a random laptop or a dev machine or on Jenkins, you don't have all these concerns that you would otherwise have, especially with like 10,000 different Jenkins jobs. And one thing I just want to stress, because a lot of people are running like Jenkins in Docker, and that's not what we're doing. We do run just regular Jenkins machines. And the point of the reason we're doing this is just for the reproducibility of pushing and it just works. We also have a lot of projects, we built a lot of system packages. So for example, like Debian packages that come from Yelp tools, we build a Debian package and that's how we deploy it. So we'll often have a Jenkins pipeline that starts and then it forks out into 4 different operating systems that we're building the same package for. And then each of these is like a mini pipeline where it tests, builds, and then pushes it to the apt repo. So we find using Docker for that has been really, really successful and has made the life of our infra people much easier, because they don't have to maintain these 50 different Jenkins slaves with different configurations and catering to all these different things people want. And this is also supported by Travis and CircleCI. So if you do a lot of open source like we do, they both support Docker now. I think you have to turn on sudo for Travis, but Circle, it just works. So you can launch Docker this way. You can even use Docker Compose. and that's a pretty nice way to do testing. So at this point, like in our introduction of Docker at Yelp, we've got Docker working pretty well in test, and we're just thinking, how can we use this in development? How can we take these benefits we've seen in test and use them while we're writing the code? And so just a little background on the way Yelp developers work. We have these things that we call playgrounds. And a playground is basically, you can think of it like a sandbox where we have all of the different like microservices that are used to run Yelp. So if you think of like the Yelp service or like Yelp.com, just serving the homepage is hitting like 30 different services. And so some of these services are just like a database or memcached or like things like that. But then there are other ones like we have like our session service, our auth service, our search service, and all these different services that serve different pages and different functions of the site. So the way developers will often work is they'll start a playground. A playground will bring up every single service, and it will just pull, these things are all Docker containers. So like we'll have a Docker database image, a session service database image. Each of these are in like separate Git repos with a Docker file. And so you can imagine if you're working on one service, you're launching like 29 other services, and all of these are just like static Docker containers, like basically the master image of like that Git repo. So one of them is like the interactive, you're editing it right now, and the rest are just basically a copy of master. And so it means that you can see things integrated really well. You don't have to like, poke at one service individually and then hope it works when you integrate them. And so yeah, playgrounds and like putting the containers there has been really successful. So like I said, each service is basically going to be its own Docker file. They're usually pretty simple. This one's, from Yelp Trusty, add the code, expose a port, run the server. And often there'll be like additional things like this one requires certain like, OpenSSL or something for some reason. So they might install system packages, but because we're doing this in Docker containers, it's very easy to just add the dependencies and not worry about like how they integrate together. So even lots of our services will run like, Ubuntu Xenial was just released. So some of our services are running Ubuntu Xenial, some are not. And there's no problem with having different operating systems between them, different dependencies, and it just works. The other nice thing about putting one container per service is that they're extremely easy to test. So not just doing the integration thing like you talked about, but even like spinning up one service and stubbing out the rest and just doing like, if I hit the endpoint here, does it give me the response I expect? That like almost like unit tests, right? If you think of each service as a unit, it's very simple to test that. And we found the testing benefits of that are pretty huge, especially in Docker. In Dev, you can link with Docker Compose, which we don't actually use for our playgrounds right now, but we are experimenting with. For our acceptance testing, which is basically like automated testing, where we link up all the services and we do integration tests where we say, if you hit Yelp.com, then we test, does the search bar appear? Does this widget appear in the bottom right? That's all done with Docker Compose, and that works really well. Yeah. And another thing that we found is it actually can be really fast. So if you're not actually, as long as you're not modifying these services, it used to be that, so for example, like the steps for creating, like bringing up a database to test against, you would first create an empty MySQL database, you would load the tables, the views, you would load the fixtures, and then once you've done all of that, which can take a couple of minutes, then you can finally run your tests. With Docker, we package all these things up, so every time you push, we just we make a Git image, or I'm sorry, we make a Docker image of the MySQL fixtured already, all the fixtures loaded. And we push that out to all the dev machines. So when you're actually running the test, all you have to do is Docker run it. That container is already pulled on all of our dev machines, and it gets updated every hour by a cron job. And so you're just running your tests immediately. You don't have to reload all this data constantly. So that saves a lot of work and a lot of time spent by devs just waiting. So yeah, in Dev, we've linked the things together. We use the separate Docker images for each thing, and it pretty much just works. And so I'm going to talk a little about like things that are not working so well or things that can go wrong and how we address those. So one thing has been like Docker instability is, we've been using Docker since 2014, so it's a lot better now than it was when we started, but certainly we've hit a lot of bugs and we continue to sometimes hit these bugs. Especially in testing, because we're spinning up, like each test is running like 100 containers. You can imagine if Jenkins is just kind of throwing these onto slaves kind of randomly, it doesn't necessarily distribute the load very well. And so load is always a concern, If you just bring up a Docker daemon and you launch 400 Dockers, you'll find that it will often deadlock or it will just crash. And that's something you have to be concerned about. Another issue is the build times. So because of the way the Docker file system works, where you have like base images, and then on top of those you have layers that add like, so you start with Ubuntu at the top, and then you might add like some packages, and then you add some configs, and you have like these 10 different layers that might make up a Docker image. That file system can be really, really slow if you're doing things like appending to large files, because it first has to copy the entire large file to like another layer and then append to it. So build times can often be really bad, and there was some bug, and I think it still exists in the file system, where parallel operations can be really, really slow. So we find we'd launch like 10 builds in parallel on like a really beefy machine, like 32 cores, tons of RAM. It should be able to handle this pretty fine. And it will take longer than just running the job 10 times in a row, like sequentially. So something to watch out for, especially if you're doing lots of file system operations. One thing that we really like to do is use base images because they can eliminate these file system operations. So because we're building lots of Debian packages, lots of system packages, we often find that we're installing the same dependencies over and over and over before we actually start building. So for example, with Debian packages, you're always installing build essential, and you're always installing like dev scripts and all these same packages that you always install. If you make a Docker image that has all of these installed, you deploy it everywhere, you just run it, you already have these installed, and you're not every single time you run a job wasting time installing the same dependencies over and over and over. And this also helps avoid the issue where you're doing lots of file system operations, and it can keep Docker a lot faster. Yeah, so it's a huge I/O reduction. We really recommend doing this. We don't necessarily use like these like fat containers with lots of things installed that you don't need in production, but especially for building, for testing, for development, it works pretty well to have like kind of fat containers just because they're pretty cheap, right? Another thing is that distributing images can be really hard. We don't use like Amazon's container registry or Google's or anything like that. We started just running like the generic like private Docker registry on premises, but it turns out it doesn't like being hit by like thousands and tens of thousands of machines at the same time, and that's pretty understandable. But when we started like, okay, so we're going to need to put a load balancer in front of it, and it's going to be backed by S3. This can get pretty complicated pretty fast. One thing that we're experimenting with right now, and that seems to be really promising, is just tarballing the images and sticking them on S3. And since we already have these cron jobs that pull the same, like the base, like, the 20 base images that we're using all the time everywhere, or maybe a little more than that, those are already being pulled hourly by a cron job by just doing Docker pull from a registry. We can just pull those from S3, like extract those tarballs and import those into Docker. And of course, S3 is very, very good at scaling to thousands and tens of thousands of clients. Because our infrastructure is mostly in AWS anyway, you're not paying for the bandwidth of pulling from S3, you're only paying for the API operations. So it's very, very cheap and it's very reliable. So then one other issue that we've had with these layered images where you have, like I said, Ubuntu on top, and then we have like a Yelp Ubuntu, which, installs some Yelp packages, sets up our app sources, sets the DNS, things like that. We might then have like a, Python service below that, which is installing Python. And finally, we'll have like the session service, which is at the very bottom. So it's on top of like these 10 different layers. So problems we see with this are that our builds are not reproducible. Because if any of these like base layers, like the layers below changes, those will be incorporated into your top level if you rebuild the same. Like just checking out the service and going to like, git tag whatever from like a month ago and building it, you'll get a different container than you did when you built it a month ago. And that can be good. So imagine if there are security updates in the like Ubuntu Xenial, then you'll get those when you rebuild it, and that's a good thing. But it can also mean that you can get breaking changes sometimes. It doesn't happen often with the base images, but sometimes with our own images, if we're not very careful, you can introduce a breaking change such that when you rebuild the same like git tag or same git commit, it doesn't work anymore. So you can't always just revert, right? Like if you're deploying applications, you probably know like the best practice is often to pin all of your dependencies. So that if something breaks, you can always revert, fix it, and then push again. For Docker containers, you can't always do that. And I don't really have a good solution for this besides just kind of watch out for it. Try not to break your base images and be very careful. So yeah, so devs are now working with hundreds of containers. Test is working with millions of containers. But we're hitting a snag now. And the problem is that we can't kill our containers. So if you've done a lot of like Docker running interactively, this probably looks really familiar to you. Like you spam Control-C, you hit Control /, nothing's working. So you open another terminal, you Docker PS, you figure out the ID, and then you Docker kill it. But this is not good for development workflow. If we're putting developer tools or like running tests in Docker, we want devs to be able to treat it just like any other process. They should be able to hit Control-C to kill it. They should be able to hit Control-Z to send it to the background. It should handle standard in. It should handle standard out. Everything should work just as they expect it to. And so this is the thing. Like we often show people this, and they'll say, "Oh, this is easy to kill, right? I'll just hit Control-C. It's just bash." So does anyone know how you would stop this? It's a trick question because you can't. So Control-C will not stop this. You can load it up on your laptop if you don't believe me. sig term will not work. If you open another terminal and you do docker kill -- signal equals term, it will not kill it. Closing your terminal doesn't work. You'll get it off your terminal, but it's still running in the background. The only solution to this is to do a docker ps, look up the container ID, and then do docker kill. And that will send it a sig kill, which is like a fatal signal, so it will immediately stop your container, doesn't give it a chance to do cleanup, doesn't let it like basically clean up. So this can be really messy. This can be really messy, and it often ends up with like killing containers that you don't have to, and it makes interactive development really hard. So the way we've solved this is with a project we call dumb-init. It's an init system for Linux containers. It's a very minimal init system designed to run in Docker containers. Yeah. So the key idea of dumb-init is just to make processes in Docker behave like regular processes. So a little background on what is an init system in Linux, in case you're not familiar with it. The init system is just the very first process. So when you boot up, like if you take a traditional server and you boot it up, your init is something like sysvinit or like systemd, which is everywhere now, upstart. So it's just the thing that you're using that starts your first process, or it is your first process, starts your second process and all your other processes. It often has additional things like supervising your apps, but that's not a requirement. So dumb-init, for example, does not supervise your process. It will not restart it if it stops. All dumb-init is doing is starting your process and kind of taking the responsibilities. So the responsibilities of a traditional init system are just launching the initial processes, and then the second two are things people don't think about as much, waiting on orphan zombie processes, and I'm going to talk about what a zombie process is shortly, because that's not obvious, and then also forwarding signals. And so the question people ask is, do containers need an init system, right? People often think, oh, my container, everyone says container should run one process only. And the way we think of that is containers should do one thing, not necessarily one process. So our approach has been multiple processes is okay, but we still try to keep our containers doing one actual thing, and we'll explain why that is. So the first problem I'm going to talk about is signal forwarding, and this is the one that's most applicable for like, Control-C doesn't stop it, Control-Z doesn't send it to the background. So the way signal forwarding works on Linux without Docker is if I have a process ID 1234, and I just do kill 1234 in the terminal, it's going to send a term signal to that process, and then each process has a table, so for each signal, it has a table that basically says, when I receive signal 1, I'm going to do this action. When I receive signal 2, I'll do this action. And if a process hasn't specified a custom handler for this certain signal, the kernel has things that it will fall back to. So for the term signal, your process will die if you haven't specified what to do. But you can also specify to do different things. Like, for example, if you're in Vim, for example, when you hit Control-C, it doesn't actually kill Vim. Vim actually intercepts that signal and does something intelligent with it. So these are signals that you can catch, but that don't have to be catched or don't have to be caught. So if you do not catch them, they will fall back to default behavior. When you're in Docker, though, this happens differently. So if I send a term signal using docker kill -- signal, that sends a command to the Docker daemon, which then sends a term signal to my process. Because my process is process ID 1 inside the container, it's acting like the init system, and the kernel applies special behavior to the init system. So if you're receiving a signal in your table, you have not specified custom behavior, the kernel will not fall back to the default behavior. So if your process has not specified what it wants to do when it receives a term signal, the kernel will not fall back to just killing the process. It will just do nothing. It will bounce right off. So that's why you end up with these signals like sig kill, which cannot be caught. All of the signals that cannot be caught will work. Signals that can be caught will not work at all unless they specify the custom signal handler. And that's just a special case in the kernel for PID 1. That means you can, if you run Python, you can imagine that the Python might actually be a server in practice and not necessarily just like a while true pass loop. You'll send signal term, nothing will happen. You can run this command as many times as you want, it'll just spin. And so people will say, well, okay, not everyone can be doing this wrong, right? Aren't people stopping their containers? And mostly people are just sending sig kill. That's what docker stop does. If you've ever run docker stop and you notice it waits, I think, 10 seconds, and then eventually your container dies, what's happening is that docker stop sends a sig term, then it waits 10 seconds, and then it sends sig kill. So often people will not even realize that. They'll think their container is like stopping right now. It's really just sent sig term. Nothing's happened at all, and then it's waiting to eventually kill it. So eventually people are basically just using sig kill in practice, which has a lot of problems. Like for services, imagine you're in the middle of serving the Yelp.com, like serving the homepage, and your connection just dies in the middle. That's a really bad experience. It might also leak, like if you have open connections to your database, for example, you can leak those, and that can be really bad. And of course, for interactive tools, it just doesn't work at all because you can't hit Control-C, you can't send it to the background. So the way dumb-init fixes it is it adds this process at the front, which basically every time it receives any signal, it will just forward this on to your process, which is now like PID 2 or 3 or something. And that's all dumb-init does. So it means when it receives this term signal, it forwards term. It doesn't die itself. It just forwards it to your process. Because your process is no longer PID 1, there's no special case in the kernel. So if your process hasn't registered these custom signal handlers, it will just die. Dumb-init is just waiting for your process to die. It will exit with the same exit status as your process, and then you're done. That's all dumb-init does. It's very simple. It's like very few lines of C code. The second problem that init systems are supposed to solve and that you don't get in Docker if you don't use an init system is zombie processes. So what are zombie processes? So you'll often see, like if you do PSOX or something and you see zombie processes, people will often not understand what these processes are. So if you like Google zombie process, you'll see like Stack Overflow, how do I kill a zombie process? It turns out zombie processes cannot be killed because they're already dead. So a zombie process is just something which is no longer running, but which has not been reaped or had the wait system call called on it by its parent. So that means it's exited with an exit status. So like if you run a command, it has an exit status like 0 on success, non-0 on failure. So the command has already finished and reported its exit status, but its parent has not yet called wait on it, which means it has not yet learned of the exit status. So the kernel is basically keeping track of this process. It still has a PID, it's just not running, until the parent calls wait so that it can still learn that exit status. And this is totally normal. This happens every time a process exits. The thing that's not normal is that processes, like parent processes, will usually call wait immediately, which is why if you do PS, you'll usually see you don't have zombie processes. So if everything is working properly, you won't have them. Like you won't have these zombie processes. So for a typical Docker service, it would look something like this. We might have like Python running as PID1, and then we can imagine it spawns like a bunch of worker processes, and when a request comes in, it just gets handed off to one of these workers to actually process it. So let's say, for example, your worker process for some reason has launched some other process. So in this case, we're using ImageMagick. We can imagine like, you've uploaded an avatar and we need to convert it to PNG or something. So imagine this has launched like ImageMagick. ImageMagick exits, but for some reason the worker has not called wait on it, has not reaped it. This thing will become a zombie and it will stay a zombie. And besides existing in that process table, there's not really any concern about having zombies. It's just something that's still in the process table, still using a PID. So then eventually if this worker process exits, the ImageMagick becomes an orphan. So orphan processes are always reparented under PID1, the init system. So this means the parent is now PID1. And there's the rule basically for init systems that the init system is expected to, whenever it receives an orphan process that is a zombie or becomes a zombie later, it should reap it. And that's why when you have these orphans that become zombies, they will always be reaped immediately on your laptop. Like you'll never see a zombie parented by PID1 basically, except in Docker. So you can end up with this case where like, this is just a fake Python service that I run. And you can see that it's spawning Pythons and convert, which is ImageMagick. You can easily build up these hundreds and hundreds of zombies. And by default, you only have like 30,000 process IDs. So if you're doing this and you're running these services for a long time, you can actually run out of process IDs because these are still using process ID numbers and entries in the process table. So if your service doesn't wait on random new children, and like, why would your Python service that's serving a web page do that? Then these zombies will basically exist forever until you restart the service. So correct init systems, and dumb-init is one of them, or at least we hope it is, expect to receive these and we'll wait on them. So using an init system, a correct init system will give this to you. So dumb-init itself is like very lightweight. It's very few lines of C code. It's statically compiled, which means that you can take containers of any operating system. So you can take like Fedora or Ubuntu Debian, and it doesn't matter the version. You can just throw it into the container and it will run fine. It doesn't have external dependencies. We provide Debian packages, binaries, and Python packages for it. You can go to github.com, Yelp dumb-init, or you can just Google dumb-init. You'll find how to use it. Basically, all you do is you take your command, you put dumb-init at the front. It will launch dumb-init first. Dumb-init executes everything after the first argument, and your process will respond. So often people will set it as the entry point for their Docker, which just means that's the command that gets run first, and anything after that is run afterwards, and then it pretty much just works. You can also just prefigure commands. Yeah, so going back to like Yelp Story, at this point, now that we've solved this problem, dev and test are working pretty well. But production right now is pretty messy. So we have lots of these services, right? And we've already set up these Docker containers because we really like using them in dev and test. but in production, we're not really using them. And we have all these microservices, but the way you actually do these microservices is by going to this track page and looking at these crazy instructions. And if you actually click on this, it'll be like, okay, how do I deploy a service for the first time? And the first will be like SSH2, ad hoc to SFO2, blah, blah, blah. And like run these 10 commands and get like someone who's privileged to run the commands. And so everything is extremely manual. And it turns out that when things are very manual, people don't use services like they would if they can do it easily. And so because we have 300 plus engineers and lots of services, we want to make sure that deploying services is as easy as possible and encourage people to work in them because it makes life a lot easier for everyone. So this is where we're going to talk about PaaSTA. And PaaSTA is like a PaaS or a PaaS that's designed for Yelp. And I'm going to talk a little about the design goals for PaaSTA. PaaSTA is an open source project. You're welcome to like start using it. But I'm going to focus more on like things we get out of PaaSTA, the benefits we see, why we designed it as we did, in the hopes that like you will maybe take some of these principles when you design your own. So I'm not necessarily trying to sell you on PaaSTA itself, but more the principles of PaaSTA and how we think it should work and how it does work. So first we thought, okay, what's the problem that we're trying to solve? Before we go designing it, we want to make sure we address all these issues. And the key problem is that developers spend a lot of time trying to ship working code. Like that's the main problem at Yelp right now. We have a monolith right now that we're trying to split into services, but it still exists. And often developers will write code. Say like one day you write the code, the next day you get it, shippeted, you do the code review, everything's great, the code works, and you want to get it to production. But the problem is there's like 50 other developers who also want to ship things to production today. And so we end up with this push process that involves 20 different developers get in a branch. This branch goes to stage. All these humans go to stage and verify their changes. You can imagine getting 20 humans to go to a stage environment, verify their changes takes like an hour, even if you have all these things scheduled in advance. Okay, everyone's verified on stage. Now we need to build it, send it to prod. So that takes another 20 minutes just to get like onto Canary and prod. It will marinate there. If any one of these 20 branches breaks the site in any way, you're going to have to roll back, kick out that branch, rebuild, start the whole process. So in practice, it means that developers who've written working code will spend like 2 or 3 hours just to get it to production, and that's in the case where like things pretty much work. If things go badly, you may need to wait a day or 2 days to actually get your code to production, and that's way too slow. The deployment is manual, slow, and buggy, like that speaks for itself. And we're not reusing those great containers that we've already set up. They already work, we know they work, we test against them. So it means that we're wasting all this time testing the things that are not even going to prod. The code is going to prod, but we're testing the containers that do not go to prod. It'd be great if we could reuse the same containers in prod because we already know that they work. We know that if we hit them on this port, they respond with what we want. And new services are very difficult because it's involves SSHing and like 20 manual steps just to get them deployed the first time. So the key idea behind PaaSTA is that we want to empower our developers to work faster, to spin up new services, to not be blocked on like operations issues. Then the other thing with 300 plus services, you can't have your operations people be experts in all of them. Like there's no way, the operations people are great, but they can't know how, if they get paged at 3 a.m. in the middle of the night, they can't wake up and fix random service 227, right? So the idea is that these engineering teams should own their own services, and then the operations people will just own like the core infrastructure. So they're going to own like the Mesos cluster that this runs on. They're going to own services running in general, and then maybe some of the key services. But we want to make sure that engineers are free to kind of write things how they want. They're not locked into, operations only supports Python and this operating system and, these specific things. We want developers to be free to use different languages, different operating systems, different environments, install the packages they want without getting blocked and without being limited. So we solve this with PaaSTA. And like to just explain what PaaSTA is, like a very simplistically, is to say that it's a PaaS that deploys services using Docker containers. And there's a lot of those, right? There's Kubernetes, there's Mesos and Marathon. And we're going to talk like PaaSTA, the best way to phrase PaaSTA is that it's the glue. Like we did not go reinvent Kubernetes or Mesos or Marathon or anything like that. Like we very much do not want to reinvent these things. They're great and they already exist. PaaSTA is the glue that tries to make it so that these tools work well when you have a large engineering organization, lots of developers trying to ship code, trying to deploy services. So the features of PaaSTA that we get, like the most obvious one is that it runs containers in a fault-tolerant way. That's the same thing you'll get from any of these schedulers, right? That's just the base thing PaaSTA gives you. It integrates monitoring health checks. We use Sensu for that. It integrates service discovery. We use SmartStack from Airbnb, which is really nice. And then the main thing, like the thing we're the most proud of, is our config-based deployment, which is kind of PaaSTA special sauce. And we're going to talk about how that works. And so like just the criticism we often hear is like, oh, you wrote a replacement for this thing that already exists elsewhere. And we definitely did not do that. We try very hard not to rewrite things. At Yelp, we use tons and tons of open source. We try to contribute to open source. We don't like writing things in-house that already exist and are well developed. PaaSTA is just the glue that says, given all these developers, how do we make them work with things? And like, if you imagine you're using Mesos and Marathon, you can't have 300 plus developers connect to the Marathon web UI and like click buttons and spin up a service and deploy it here. Like that just doesn't work. So you have to have some kind of automation beyond just the web UI or the API or the command line tools that makes it work. And so you need lots of glue. And so the way we do this is with something we call SOA configs. And SOA configs are kind of a core principle behind PaaSTA. SOA just stands for service-oriented architecture. The idea is that we have this one Git repo that contains one directory for each service that we're going to deploy. Inside this directory, we have all the files that declare what Docker image we're going to use for this service, what kind of ports it needs, what kind of volumes it needs, where it's going to get deployed. So does this get deployed to dev only? Does it get deployed to these two stages or production? How many instances do you need? All the details about the deployment. And so the really nice thing about putting all of these details in a Git repo is that we already know how to work with Git repos. It's just like code. They're just YAML files that you edit the YAML, you submit it up to review board, you get it reviewed. We get code review, we get access control, auditing. If you make a mistake, you just roll back, you git revert, and you push, and the infrastructure will fix itself. And PaaSTA's job is basically look at this Git repo, look at all the configs, and then make them the truth. So we're just declaring how we want things to look, and then PaaSTA's job is to go from state A to state B based on these configs. So an example, like a very simple service in our SOA configs looks like this. So this is one service which is composed of two different tasks. So the main service at the top is just like, you can imagine that being like a long-running service, like this is the things people actually connect to. So we're just saying, okay, the Docker images need 4 CPUs, a gigabyte of memory, and we want 3 of those. And we support like obviously more advanced like auto scaling and things like that. But just like a very simple one is saying we want 3 instances and deploy them somehow. Then we have like below what we call batch jobs, which are just like one-off workers that process things kind of on the side. So the image processor needs 1 CPU, 2 instances, 2 gigs of memory. Its command is just going to be to process these images. And we also specify our monitoring this way. And if we had like a more detailed one, it would also say, how does the health check work? How do we know it's actually come up? What does the deploy strategy look like? What stages it gets deployed to, things like that. So PaaSTA is going to read that config, and it's going to deploy it to something like this. So if we imagine our SFO2 data center, and it's obviously running tens of thousands of containers, not 5 containers, but it's deployed main 3 times with these 4 CPUs, image processor twice. It's made sure they're spread across hosts. It's made sure that it's fault tolerant. So if one host gets killed, it will just automatically, the same thing you expect from any other scheduler. So the way we change this is we just open the Git, clone the Git repo, open the file, we delete the 4, we make a 5, we submit it, we get it reviewed, we push it. So all we've done is change that. So the way PaaSTA will do this is it will look at the state of the world, and it will do something we call the bounce process, which is just how do you go from the service in one state to another. And it's bouncing. The idea of bouncing is that you do this in like a graceful way. So what it will start by doing, and there are different strategies for this. So in the base like bounce strategy, it will bring up 3 replacements. So it's kept the 4 in place. It's brought up 3 more with 5 CPUs. And then it's going to slowly kind of drain from the old ones as all the connections die in the load balancer, and then put these new ones in, and then eventually kill those. And so we have lots of different bounce strategies. So the way we like to deploy Yelp.com is we push the new code to something like 1% of live traffic first, and then we sit there for 5 minutes. And the idea being that we can watch the error logs and make sure we haven't broken the site in a catastrophic way. Because even 1% of traffic to Yelp.com is a lot of visitors, right? And so we can watch it there, so we can deploy slowly. There's different ones where you can, throw out all the old ones immediately and then just bring up new ones, but that obviously has downtime, so we don't really use it. There's the one where you bring them up slowly. There's one where you switch one at a time. So lots of different deploy strategies or bounce strategies. In this case, this is, switching the number of CPUs is just like a code deploy looks like. So it's very seamless. There's no downtime. Yeah. So for actually deploying a service, we just use Jenkins pipelines. You saw that we're very big users of Jenkins. And so Jenkins is basically just calling out to these PaaSTA utilities. So the first thing we'll do is we'll run our tests. We'll run like the integration tests. You can see these are two-step tests. This is like the unit tests here, and the second test is integration tests. Then we'll do security check, performance check. Before we eventually push it to stage, developers will go to stage, verify it, before eventually pushing to prod. And so this is significantly faster than the process where you get 20 developers together on a branch and push it out, check it, yeah. So PaaSTA also comes with a Commandline tool, and we're really proud of this PaaSTA Commandline tool because it's how we would design like service deployment, service status, things like that for developers. So you can see we use nice colors. We link to the pipeline. We have the monitoring. Everything's integrated. Here I'm just looking at what the Yelp main service looks like in 2 of our prod data centers. So you can see it's set it's up. It's running those 3 instances I showed you earlier. It's healthy. It's not bouncing right now. It's in SmartStack, which is what we use for service discovery, and everything's working. But this will also give you lots of details about where it is in the deploy right now. We'll let you move on from the deploy, things like that. So just the results of the PaaSTA experiment at Yelp have been that we've got these more than 300 services now deployed. We started PaaSTA about 1.5 years ago. It's only in the past year, probably about half a year to a year, that we've actually started using it for most of our production traffic. So we've now got these more than 300 services, but the really great thing about PaaSTA is that we've seen, because it's so easy for developers to use, to start their services, to push it onto PaaSTA, that developers will make services that previously they just wouldn't have done. They either would have put it in a monolith and made things even worse and worse with how long it takes to push and how slow it is and how big it is, or they just wouldn't have done the thing at all. So we actually use PaaSTA internally for a lot of our dev services as well. So our NPM registry, our link shortener, our link shortener is a Haskell app, which we don't use anywhere except one guy at a hackathon wanted to write it. So we use it in dev, we use it in prod, we use it everywhere, but because it's so easy, less than an hour to create a service, pretty much all you have to do to satisfy what we would call the PaaSTA contract, which is how your app is expected to behave. You write a Docker file, you listen on port 8888, and you're done. And then besides that, you have total freedom in how your app is written, how it behaves. It's also not limited to HTTP. We've deployed a TeamSpeak on PaaSTA. We've deployed all these crazy things. I did a Counter-Strike server on PaaSTA, and it worked. So tons of different things you can do with it. You're not limited. Existing service deploys are very quick. So we've been pretty happy with PaaSTA, and just want you to kind of think of, these are the principles that we think are important. But PaaSTA itself is open source. So if you want to check out more about PaaSTA or the PaaSTA principles, the things we like, or things why we designed it the way it is, you can either Google PaaSTA. Make sure you have 2 A's and you don't just Google PaaSTA the food. If you go to github.com/yelp/PaaSTA, you'll find details on it. There's lots of videos, people who have given talks and the principles. And Sensu, Mesos, Marathon, SmartStack are not our technologies, but those are open source technologies that we use very heavily and we really like. Yeah, so that's PaaSTA, and that's my talk. So I guess I have a few minutes to answer questions if anyone has them.
Oh. I was wondering about the playground and if that is on local developers' machines and how they start that up. And we're trying to figure out how maybe developers can do that where they have one service, but we're not really sure. You have the individual repos, but where's the overall definition?
Yeah, so the way we do it is we have these centralized dev machines. So we have just a rack of them, and when on your first day at Yelp, you're assigned one and you log into it via SSH, and that's how you do all of your work. We don't really recommend that. That's just kind of the status quo, because that's how it's always been. We actually don't use Docker Compose in development, although we'd really like to. And the reason for that is just that we have some legacy services that are not deployed in Docker yet. If we could get to everything being deployed in Docker, we would really love to use Docker Compose for that. But because of the way it's the way you configure it, it's really hard to make Docker Compose interact with non-Docker services. So we have our own thing. It's called PGCTL. It's on GitHub if you want to check it out, but you probably don't because it's not that great. If you can, I would recommend using Docker Compose. If you're just starting or you have everything in Docker, I think that's the way to go, and that's the way we're moving towards.
Can you talk a little bit about why you have a single directory for all the deploy stuff rather than storing each one with its application?
So I don't think I don't think we feel super strongly about this. That sort of is the way things have always been done at Yelp, at least since we moved to services. So there's kind of precedent in that. I don't see a huge reason to keep it in one repo as opposed to different ones. Definitely just having it in Git repos, and I think putting it with the application actually makes a lot of sense. I don't think there's a strong reason either way.
I was just curious about building from the same tag and generating an artifact that's broken. That used to work. Could you explain again how that works? What's happening there?
Yeah. So, I get there. So basically, each Docker image is composed of these layers where like the Ubuntu Xenial image we don't even control. That's like on Docker Hub. It's just like the Docker people I think maintain it. They've taken Ubuntu at its current version. They've like snapshotted it, and then they've made that available to people. And then, so that's like one layer of the image. And then our like Yelp layer on top of that just takes the Docker Hub image and it makes like 2 or 3 changes, like small changes like installing a couple of packages, changing the app source, changing the DNS. And so we have all these different layers. Like then we have like a Python service, which like, for example, installs Python. And so if any one of these changes, like basically the file system is just stacking layers on top of each other. So if there's a file on the Ubuntu Xenial one, it will also appear in the Yelp session service all the way at the bottom. And so if one of these changes, that change gets incorporated. So like any layer above can break your layer down below, basically. We maintain our own. So we start with Ubuntu Xenial, which is just the Docker image. And then like the very first thing the Yelp Ubuntu image does is it changes that out for our own apt sources. So we do use our own apt sources, but because we're using that Ubuntu Xenial image, we still are kind of, we're still vulnerable to that. And like the Ubuntu Xenial image doesn't really break. Like to be honest, we usually break it ourselves. So yeah, it's just something to keep in mind.
Hi. So if a developer decides that they need to create a new service for some particular reason, are they empowered to make that happen through PaaSTA, or is there some kind of approval process?
So we do have so we have like hackathons where every single hackathon will have like 3 or 4 new services at least come out of it. They're often not like production-worthy services. They're like, a link shortener written in Haskell or like an IRC bot or something in PaaSTA. In terms of, we do have an approval process, but it's more of a design review, making sure everyone's on the same page in terms of how we're going to design it. I think if developers just, launch services without, it's basically just making sure we think about it and everyone's on the same page in terms of architecture. So they can launch services, but we do have like a policy of, getting the architecture approved.
What's the last TA stands for in PaaSTA?
I actually have no idea. It's kind of it's a running joke where like they send out these surveys, like PaaSTA user surveys, and then the last question is always, what does PaaSTA stand for? And so they'll get like interesting, submissions of what PaaSTA actually stands for. But I have no idea. I don't think anyone really knows what it stands for. Yeah.
So can you share some of the good guesses that people had? If you remember some particularly good ones.
I don't remember them.
Anyone has a question? Can you repeat that?
What kind of, so environment variables configuration, what kind? What kind of configuration are you talking about? Like an example of something you would configure? Like secrets or something? So the way we do a lot of secrets is we don't really use environment variables for our secrets. We tend to have them on the file system deployed to like the PaaSTA boxes. And then in our SOA configs, we specify which directories we'd like to mount into the container. So depending on which service it is, it will mount different directories that contain like secrets or config and things like that. That's how we mostly handle configs and secrets, is just by mounting them into the container. And that means we don't have to actually add them in at build time. Environment variables would also work, but might be a little trickier, I'm not sure. The other nice thing is that we have separate credentials, like separate secrets for like stage, dev, and prod. And so like stage and dev, anyone in the company can look at. Prod is limited to people with prod access, like more trusted engineers. So by having these same files that are just different on different servers, it's very easy to deploy, very easy to test in the different environments.
And the last question as we're going to wrap up for the next presentation.
My question is just, are you aware of any larger customers or clients using PaaSTA other than Yelp?
I don't think anyone is using PaaSTA, at least not at a large scale. It definitely is possible to use in open source. Like we have a demo of PaaSTA deployed open source. That's like our demo instance. But I'm not aware of anyone using it on a large scale right now. It's only been open sourced in the past, I think, 6 months anyway. Not even that long, I don't think. So it's fairly new in the open source. And again, like my idea is mostly just to get people thinking about the principles and not necessarily using it itself. Yeah.
All right. Thank you very much, Chris and Yelp.